Yeah, so under this recording, we'll be discussing nuclear physics, right? So nuclear physics is all about the study of the nucleus, study of the nucleus. So we'll be studying how the nucleus behaves. So the first thing that you must understand is that a nucleus is a combination of is a collection of protons and neutrons, and then that will form a nucleus. Yeah, so I'm not gonna be talking more about the theory part, but you know that when we talk about protons, we're talking about positively charged particles. Uh, so neutrons, here we're talking about what? Uh, we know that neutrons is when you have a collection of protons and neutrons, and electrons, equal number of protons and equal number of electrons. That will give us the neutrons. So now, what I want us to talk about. So these are the symbols that we'll be using, right? These ones, A for atomic mass, Z for the number of protons, and then N will be for the number of neutrons. So you guys, you know this. Yeah, I think you already know this. That A here will represent the mass number, and then this Z will represent the atomic number, and then this is our element in the periodic table. So you guys, if you are looking for an element, you know that you're gonna use this. Right. So what I want us to discuss is okay, we can just start here. If they ask you a question like this one, they say let me do this. Given a common ion nuclei which has a mass number of 56. So we know that A is equal to 56. Then they say calculate the radius, approximate mass, and the density of an ion nucleus. So you guys, you know, ion is represented by the element ion is Fe. So its mass number is 56, and its element number is 23. Let's check. It's element number 26 on the periodic table. So now I want to know its radius 26. So the formula for radius is given by r equal to r naught h exponent 1 over 3. And so r naught, it represents this, it will always be this way, right? This is the radius of a what? Of a general nucleus. So with that question, it means you guys are just going to say r is equal to 1 comma 2 times 10 to the negative 15. Then A is the mass, is 56, no? 1 over 3. Then you just punch that in your calculator. I don't have a calculator here. So, but whatever answer you get, it will be in meters. Since I decided to use 1 comma 2 times 10 to the negative 50. And then yeah, that's all about, yeah, they actually calculated it here, but they didn't do it. They wrote it here. So this is what we're talking about. The answer is 4,6. No? That's 4,6 times 10 to exponent in 15. To exponent negative 15. I'll just put your negative 15 here. So when they ask about, if they ask you about the volume, this is the formula that you're going to use. So this applies for all elements in the periodic table. So you just have to know the formula. It's equal to 4 over 3 pi r cube. Then you substitute your r. We know it's gonna be what is the one that you just calculated, at 4,6. So it's a follow-up question. 4,6 times 10 exponent -50 cube. Then you get your volume of the element F will be what 4,77. So what I want us to discuss, okay, isotopes. What are isotopes? We're talking about elements that are the same, but they have got different numbers of neutrons or the mass number. So neutrons or the mass number, say the mass number represented by A, it must be different, but we'll be talking about the same element. For an example, if I'm having Fe ion 56, but you find that now the mass number here is 55, and there's 26, and then there's 26. You see, this is different, right? So these are isotopes. Just trying to emphasize what's an isotope. So I think you guys, you know that theory. A strong nuclear force. You know that some elements have got a strong nuclear force, some they've got a weak nuclear force, some they've got a weak nuclear force. Now I want us to discuss this is why I want us to actually start the binding energy. No? But actually let's not start here. I want us to discuss the types of decay. Then we'll go back to those ones binding energy. Yeah, I want us to start with the types of decay that you must know. So let me just open a page here. What did I do? So yeah, we've got the types of decay. No? So let's start. Let me write them here. The first one is alpha decay. We've got 3 types of decay that they can ask you in a test. 3. We've got 3 types. Three types of decay. The first one that we're gonna discuss is alpha decay. No? First one is alpha decay. Then the second one, it's number 2, it's beta decay. And the third one, it will be gamma decay. So you must also know there are differences. Some of the things that you must know. So okay, let's start with alpha decay. I want you guys to understand something here before I start. Gamma decay. So I want us to first focus on so that you can understand what we are doing there. Three common types of radioactive emission, what. And this statement is very important, no? But three common types of radioactive emissions. Uh, Remember here we're talking about elements. Yeah, this term is very important. So let's start here. What's a radioactive decay? This is the process in which an unstable atomic nucleus gains energy by emitting radiation in the form of particles or electromagnetic waves. So this is where everything starts. We've got beta, we've got gamma. Those beta particles, these particles they will penetrate up to 3 millimeters of aluminum, and then gamma will penetrate several centimeters of lead. So what you guys have to understand is that beta, gamma, and alpha, we're just talking about types of particles. Né? So with the decaying, it means how long will that like what will happen to the nucleus? How will it lose its energy when it enters a particular medium, such as this one? You see, yeah, that's why you have got this diagram. You have one, two, three. So these are the types of mediums. No? The first medium is paper. You have glass, you have lead, and then you have got an alpha particle, which is alpha. You have a beta, and then you have a gamma, which is R. So they are entering different types of media. So each each one of them they will have a particular radioactive decay. They are gonna lose energy different. So you see here they say this one it wins. Right? It means the gamma particle. It means it penetrates the materials easily. Penetrates the material easily. And so we're talking about the types of decay down there. So let's just talk about them here. So we've got alpha decay. So with alpha decay, so you must know how to actually find elements and apply these decays. So let's talk about the first one, alpha decay. So generally, if we're talking about an alpha decay, let's say you have got an element X with a mass number, and here let's say it's Z for proton. So our element is going to lose the number of neutrons. So I just want to get an example here from your slide. Yeah. So if it undergoes alpha, if any particle goes under alpha decay, you're going to have a new element will be formed, and a helium atom will be released always. So this will always be the case. So the mass number, it will decrease by 4, and the proton number will decrease by 2. So yeah, because this will always be the case. Reason being, if a helium atom is emitted, yeah, a helium atom is emitted, that means we already took 2, and if the number of neutrons, remember that this one represents the number of neutrons, if they are going to decrease by 2 every time and any particle undergoes alpha decay, it means if this is decreasing by 2, it means that we have got 2 plus 2. which means the mass number will decrease by what? By 4. So the mass number here decreases by what? By 4. And if you check, this equation is balanced. A minus 4 plus 4 will give us A, which is this A. And Z minus 2 plus 2 will give us what? Z. So we've got this equation is balanced, which just tells us that this applies on any particle. So for an example, on your guide, you are given this example. You're given radium, I think. Yes, it was radium, which it had a mass number of 226 and the neutrons 88. So we know that a helium atom will be emitted. So this is always the case. And then they will ask you to find the elements that will be there. So what you can first do is you can just put any variable, let's say x, and then you say I'm gonna decrease this one by 4. So 226 minus 4 will be 222. Just put 222, and then this one is decreased by 2, it will be 86. So go and look for element x on your periodic table. You will find that element number 86. Let's just check it. That, so that's why you have got the periodic table, and they should give it to you. What is that table? You just go up and find element number 86. Yeah, so here we go. So this is element number 86. It's a radon. So you're just gonna say Rn with the rosters X. It's a radon, and then 88 is called what? So that one was a radium. So you'll just put Rn, then this 86 plus the diameter that was emitted. That's all about the alpha decay. So it will always be like that. You can also go and do this example and see and check if you understand. Let's say you are given, yeah, let me use this one, uranium with a mass number of 238.92. Then it undergoes alpha decay. So you will just find this element. This one will not always be like this. So I guess it means your duty is just to subtract here by 4 and get to 34. And then here is subtract by 59. So it means the element number 9, the periodic table. So go to the second type of decay, which is the one that people don't understand. Beta decay. So this one is divided into two parts. I've got beta plus decay, and also have beta minus decay. So you must be able to tell. So let's start with beta plus decay. Yeah, let's start with beta plus. So what you have to know are the properties. So under beta plus, so under beta plus, you have to know that a positron will be emitted, which is represented by the letter V, and then a neutrino will be emitted. So what do you mean by a neutrino? Is just the smallest particle of matter. Ne? So its mass number is very, very small. Even an antineutrino, which will be emitted on the beta what on the beta minus decay. So these are the two properties that you must know. And then another thing you have to know is that the number of neutrons, they will increase by one. Let's just say the number of protons will decrease. Yeah, write it here. The number of protons, and we know say protons represented by the letter A, they will do what? They will decrease. So let's say you are having this now. Let's say you have got a carbon, which is seen with a mass number of 10. Its a number of the neutrons, it will be 4. So if it undergoes a beta plus decay, so this will become, we know that we'll have a positron, which is represented by what? By this. So a positron, I forgot to write it. No? It will be represented by this positron. Or actually, so V represents the neutrino, not V represent the neutrino. Then the antineutrino will be represented by V bar. Then with positron, it is beta. You just write this beta and 0, 1. So I'll explain this. So here we're gonna have what? We're gonna have a positron which will be emitted, which will just be V, and then our neutrino, will have our neutrino, which is V. So this one is our neutrino. This pen. This one is our neutrino emitted, and then we will have our positron, which I said is just beta 0, 1. So now the duty is to do what is to get the elements that will be formed here. So I said the number of protons will decrease. I said they will decrease. Yeah, they will decrease. So remember that here we're having what? 10 as the mass number, 4 as the number of neutrons. So 10 minus 4 will give us 6 protons. So they will decrease by what? Under beta plus, because we have this positron being emitted. It means one proton was given out. Let's just say it was lost. So therefore, we're going to have 5 on this element. We're going to have 5 protons. And then the mass number, it will remain the same, obviously. So which means, so if you check this equation, it means that what? It means if you say 5, I think this one should be negative, the one for the positron, that the equation can balance. 5 plus 1, 5 plus 1. No, yeah, it's 5. So 5 plus 1, it represents what? The number of protons, which is 6. Yeah, so this equation is balanced. 6 protons. So that one, this one was for what? For beta plus decay. Then beta minus. So you must also know the properties. So they're the opposite of each other. So here, an electron, not a positron here, an electron will be emitted. And then also an antineutrino. So this one, it is represented by beta by the letter what? And the electron will be emitted. So that this one will be E, and that one will be minus. This slide of yours, let me see here what they were using. Let's check the variables that they used. Oh, yeah, on your guide they are using for neutrino and anti-neutrino was still fine. Well, fine here. The one that we're doing, we said the neutrino was being emitted. So it's just V. And then an anti-neutrino it's V bar. So yeah, this one it's our what? Electron. And then this one is our positron. So as you can see with this one, we're having radium and then an electron was emitted. So when an electron is emitted, it means that this one, the number of protons will increase by 1. That's why here you are having 89. Yeah, so I think this one is a good example, but let me also write. So let's first complete those properties. So I used the letter beta here. I was using my own notes. So here, let's just put whatever they are using here on the guide is E plus, and then this will be 0. So that means and it will be plus 1 here. Mass number is 0 plus 1. So it means you will just put, let's use the letter E instead of B, so that I can be consistent with what is on your guide. Positron. So this one we're gonna say, instead of saying a neutrino will be emitted, we're gonna say what? An anti-neutrino will be emitted. Anti-neutrino emitted, which will just be V bar. Then here the symbol will be E0 minus 1, and then here the last one, the number of neutrons will increase by 1. It's also a specific decrease by 1. The number of protons will increase by 1. So for an example on this one, let's say you are having for beta minus decay. Let's say you've got the element Rm, beta plus. I wanna get an example here from your guide. But let's just take any element. Yeah, let's say you have helium. Yeah, this one can do. Yeah, let's say you've got the element helium. We know that an antineutrino will be emitted and also an electron will be emitted. So this is our electron being emitted, and this one is our antineutrino. So make sure you write these things. So yeah, because there is an exercise I'll show you. And then here, it means we're gonna have what? It means we're gonna have an element which I don't know. Let's just say it's X for now. So the number of what? The mass number will remain the same, but the number of protons will increase. So this will be 3. And if you check 3 plus -1, it will give us 2. So the equation is balanced. And also this one. For this one, what happened on this one? positron is lost. 5, 1. I don't know why this doesn't balance. Let me check here. Plus 1. Positron. Oh, yeah. We actually did the opposite. Yeah, so this one is the one for beta. Let's correct the one for beta plus. This one is fine for beta minus. This one it had a problem. So we're supposed to subtract 1. So we must subtract 1 from that 4. Since here a positron is emitted, which is that 1 plus 1. So this means we're going to decrease the number of neutrons by 1. That's why here it's going to be 3. Yeah, so the equation must balance. Then you left 3 plus 1, which will be 4. On beta what? Number of protons will decrease by 1. Yeah, so you see, the number of protons have decreased. Actually, let's say the number of neutrons. Let's not say the number of neutrons has decreased by what? By 1. And then here the number of neutrons has increased by 1. So this increase is due to what? Is due to this electron because it was emitted. That's why now there is increase in the number of what? Of neutrons. It means we're having more protons. And then let's do the last one, the last type of decay, and then we're done. The last type of decay, it's a gamma decay. So this one, the only thing that you have to know is that an alpha, a gamma particle will be emitted. Let me just check for. Then another thing that you should know, no change in the yard. There is no change. Here there is no change in what's in the nucleus. There is no change in the nucleus. So these questions they can ask you in the multiple choice in the nucleus of our atom. So meaning that the mass number remains the same. The mass number will remain the same. And then and then with in terms of penetrating ability, remember that this one the symbol is R, and then for the first type of decays that we did for alpha, remember that the symbol is this. For beta decay, we're using can use this. Yeah, then this one is gamma decay. So here, in terms of penetrating ability, this one is the highest. It's just the highest penetrating ability. And another thing you have to understand is that the proton number and the nucleon number will remain the same. Remain the same. So when we talk about the nucleon number, it's not about the mass So I basically repeated, but fine. Yeah, so let's go through an example of this. Let's just take it here. I want us to be consistent with your slide. So let's just check the. So you guys will also check the examples here. If you don't understand, you just ask. So this is an example for gamma decay. We have got this element. I think it's a titanium, something like that. So it's Ti with the mass number 208 and then proton number is 81. The neutron, the number of neutrons is 81. So the number of neutrons will be the same. Nothing is emitted here. Or the only thing that will be emitted is the particle, the gamma particle. So it will always be like this. So if it was helium, helium has the mass number 42 and it undergoes gamma decay, it will just be He24, just add R. So what they will do is they will just tell you to fill in the missing elements, right? Just like in this example. You see the first one, they say identify the unknown nuclide of what? So letter A, this one and a gamma particle is emitted. So we know X will just be what? So they wanted you to identify what's X. So this one is the easiest. We'll just say Ni 6528. So that was the answer. 28 Ni plus R. So that was the answer for X. Then this one, as you can see, an alpha particle is emitted. So this alpha particle here, it's what? It's He24, this one. And then they want you to find the X. So you're going to subtract 4 here, and then here you'll add 2, meaning you're going to have, I don't know, you're gonna check on the periodic table what is the value of X. So we know that our new element will be 219, then 86, and then you look for this element. Then this one is beta what? The one that is a positron being emitted. One that is a positron being emitted is beta plus decay. So we are talking about beta plus decay here on this example. So this is beta plus decay. So we know that on beta plus decay, a positron is emitted and also a neutrino is emitted. So your duty was to find this one. So to find X, it's very easy. We know this was going to be 55, and then here you just do what? You just 26 plus 1 will be 27. So you look for element number 27 on the periodic table. Yeah, you're gonna look for it. And then you will also do the other ones, the other examples. So this way, the remaining ones you'll go and identify which nuclear reaction is taking place. Yeah, you just do. Okay, so with this one, you know that this one will say it's beta minus. Then with this one, it's alpha decay. Then this one, it's beta plus. With this one, an electron is emitted is beta minus. Then with this one, it's what is alpha decay. Yeah, so I've answered everything there. Then let's go to mass defect and binding energy. Mass is closed. So this is the last part for today. So we've got the concept called binding energy of an atom. So we're talking about the energy in the nucleus, binding energy of an atom. So when it's like this, we're talking about the energy of an atom. So it's equal to change in m multiplied by c squared, whereby this one is what we call the mass defect, and this one is the speed of light. So this formula is used to calculate how much energy is in the nucleus. How much energy is in the nucleus. I will forgive the handwriting, guys. I just want us to wrap up these things. Then we change in m. We know the formula will just be what the formula is given by the number of. I forgot it. It's m. Let me just try to write it first. Maybe I might write the right thing. The number of protons plus the number of neutrons minus the mass number. Let me just confirm. Just confirm. So we skipped that part. So this is the only part I skipped, you know. So now I'm going back to it because it's the easiest. Just have to not calculate using that formula. And what? Okay. What is that part? So the story, guys, you're gonna check this here. Yeah, this is the binding energy and nuclear force. So this graph, you see this graph here, it just represents the energy of different elements. So they just said that to represent everything in terms of the graph. Lithium, Be, what, see. So this then here they were this part represent the mass number, then this part represents the energy. And don't forget energy is measured in MeVs, in atoms. Those are the units, MeVs. MeV, let's just say MeV. So this is the formula, no? It didn't, yeah, this part. This is the formula for binding energy. Binding energy is given by the number of protons plus the number of neutrons minus the mass number, and then this is the change in m, and then this 931 that you see here, this one is the speed of light. So if you'll be using maps, you're not going to use the one that 9 times 10 to exponent 8. If this part is in maps, you'll also put this one to be in maps, so that this one is c squared. So there is an example here. No? Let me see if I can actually. So if you'll be using 3 times 10 to exponent 8, you see, or the units for mass must be in kg if you're going to be using this one. Let me see if there is an example for the one whereby they used. So if you will be using 931, you'll just put where there is c squared, exactly where there is c squared. Isn't it that you have this formula changing m times c squared? So here, everything, you'll calculate a change in m, which you know that is simply a plus n is minus m mass number, multiply by just put 921,494. And then you get your EB, binding energy. So this is an example. So the units for, if they give you a mass in what, I forgot this unit, in U, the atomic mass is what U. Yeah, but if they give you the mass as the units being U, if your mass, this is the mass of the element helium. If the unit is U and not kg, then you're going to use your C as 91, comma something something MEV with the rest squared. And so that's all about nuclear physics. And then another thing that you have to know here is this formula. There is this formula, it's very important, is to calculate how long the atom will decay, will undergo decay. What is that formula? I cannot find it. Just this one. Let me explain it here. So you have n equal to n initial e negative lambda t. T for the time. Then this one is the decay constant. Then this one is the initial what, radioactive nucleus. Let's just say initial number of nucleus. Then this one will be the final number of nucleus. Sometimes they're gonna ask you to calculate. Let's say they say calculate the time. Sometimes they're just gonna say calculate the radioactive nuclei. So when they say this, you have to know you are calculating for n, then for time is t, and then if they say calculate the decay constant, which they will be referring to lambda, calculate the decay constant. So it will depend on the data that you are given, and then I can also say calculate half-life. So this one is a, if they say calculate half-life, so this one you'll have to know the formula. Half-life is T half. Let's see if they wrote it here. They didn't write it, you'll have to find out. Yeah, it's this one. So this was, they were deriving it. So where there is T, this is the what, I can say the proof, half-life, half-life, proof, an atom. So what they did, they just said, let's see, they just said, because we're talking about the half-life, so the final will be half initial, and then T will be T half, and then they introduced a no, they just cancelled these two. Then you are left with half of equal to e to explain negative lambda t half. In order to get that one, just introduce lean. Yeah, they introduced lean both sides. They introduced lean. So obviously, lean of e will be 1. Then they remain with what? Yeah, they just remain with this part, because if you do the lean of this one will come down. You'll have negative lambda t half, and then lean of e. Then this part will become 1. Yeah, and then that hence they were having this, and then 2. So if they ask you to calculate the half-life, just know they want you to use this equation. T half equal to lean of 2 over lambda. So if lambda is not given, which is your decay constant, means you must use which formula? Let's see if we have it. The decay constant. Uh, it means you'll use this formula. Probability of decay per unit time. So this is lambda, probability of decay per unit time. So yeah, but in most cases lambda is usually given. So the last thing that you guys must know, it's fluid mechanics. So this one is a very long topic, but let me just explain a bit. But I would like to do a separate video for this one, because there's a lot of content. But fluid mechanics, all in all, it's all about the pressure of fluids and gases. I'll do a separate video of this when I have time. And you have to understand the types of what we call the Bernoulli, of the Torricellis. We have viscosity, we have a Torricellis law. So here it's all about knowing how fluids are flowing using different equations, and we'll be measuring different things. Sometimes we'll be measuring the viscosity of the fluids. Sometimes we'll be measuring the speed. So with Torricellis law, it's all about getting the speed. With Bernoulli, this one is all about the pressure. You can see it's more about P, E. Yeah. And also I have the last one for the cell. Even this one is about the pressure. The formula is F1 over A1 equal to F2 over A2. Okay. This one it will need another